I want to talk a little bit more about this idea of a growth rate, especially in the context of an exponential model. So that's either exponential growth or exponential decay, depending on what exactly we're talking about. So the fundamental idea when talking about any of these exponential models is that the rate of change of whatever we're measuring. So I'm going to talk about populations, but this could really be anything. So the rate of change of our population is proportional to the population itself. So the rate of change is equal to some, in this case, fixed constant times that population. So as the population increases, not only is the population increasing, but the rate of increase of the population is increasing. And that's going to make the population increase even faster. And then this whole thing feeds into itself and gives rise to this thing called exponential growth. That's where this comes from when the rate of increase keeps increasing at an increasing rate. Okay, so what we want to talk about is what exactly this looks like, or another couple of properties of the solutions to this. So as we've seen before with our differential equation solving, the general solution to this, the solution to what P should be, is some initial constant times e to the kt. So again, this k is typically going to be some fixed number that comes from the context of the question. It gives us a sense of what our units are for our time t. But this p0, this p naughts, is typically our starting place. So we might start at a certain value here, and then our exponential growth should look something like this. And what I want to talk about right now is this idea of a doubling time or a half-life, depending on what k is. So a property of exponential growth is that however long it takes for the value of the function to double. So notice that if we started with our initial population is here, the time it takes to get to twice what it originally was, so however long that is, whatever this time interval is, I'm going to call this capital T, that same time interval is going to take our is going to double it again. So when we came from our 2 p naught, that's going to take us up to 4 p naught. So 4 times our original after another one of these time intervals. So last time I asked you to talk about finding a way to calculate the half-life, and most of you, the way that you did it was you plugged in a certain temperature that you were looking for into our solution to the differential equation, and then you solved for what time makes that work. I just want to point out that there's another way of finding this half-life or doubling time units. So find this time t, capital T, for which it takes over which it makes our exponential function double. And the question is, all right, when is the population twice its initial value? Well, that's going to occur when this portion of our equation equals 2. So we can just solve 2 equals e to the power of kt, take the natural log of both sides, and we're looking for a time, so we're going to divide by k, and that's going to give us some time t, which is going to be our doubling time. If our k is negative, we're in a situation where we've got exponential decay. Rather than talking about how long it takes to double, we'd be interested in how long it takes to half, because it's decreasing. But this formula would get a negative time, but if we put absolute values in front, this is going to make this a positive number, which means that this is going to be either doubling time or half-life. So if you ever looked up the formula for calculating the half-life, it's going to be this thing. But what this comes from is this is the particular time, the particular amount of our t units it takes to make this exponential term become a 2. Okay, I wanted to use this. I want to switch over to a Desmos demo. Great. Okay, so what we have here is this exponential growth, and I'm just saying that our starting point, our starting population is 1, just to keep things a little bit easier. And I can adjust what this k value is, and that's going to change what our doubling time is. So if I move this up and down, if I increase the k, that's going to decrease the amount of time it takes. So if k is bigger, we've got a more extreme exponential. It's going to be a steeper sloped exponential. And if I increase this to something like 2, it's going to be an extremely steep exponential. And sort of the analogous of part of that is that, well, the amount of time it's going to take for our function to double is going to be a really small thing. If we're back down to something like a k of 0.1, our doubling time is around 7, so 7 minutes. So I also want to plot a few points here. So our original point is 0, 1. If we weight this 6.931 time units, that's going to mean that our total amount of time has doubled. And if we had another 7 minutes, it's doubled again. Another 7 minutes, it doubles again to 8, etc. And so this is a fundamental property of how exponential functions work. But in the next video, when we talk about logistic models, this k is actually going to be changing. So in this case, k is fixed. This is some property of this exponential growth. In the future one, k itself won't change, but the proportionality coefficient part is going to be changing. We're going to see what happens when we allow that to happen.